PhD student at the University of Sydney. My supervisors are Moritz Merklein and Professor Benjamin Eagleton. So this work is a collaboration between the University of Sydney, the Harris Corporation, and the Australian National University. And this work is titled A Broadband Phase Shifter based on stimulated Brillouin scattering and RF interference. So just to remind everybody, a phase shifter is a device that induces a phase on a signal waveform. And these are useful for lots of different things, but one of the main applications is in phased array antennas. And these are useful because the main lobe can be steered by controlling the phase to each individual antenna element. And this is particularly useful for things like satellite communications as well as medical imaging in the context of MRI machines. So currently phase shifters are implemented electronically, but these have a number of problems, being that they've got limited bandwidth, a relatively low operating frequency, and they're vulnerable to RF interference. So this gives us a pretty strong motivation to move into microwave photonics, which has a broad bandwidth, it's immune to electromagnetic radiation, and it has a high operating frequency. But we also want to maintain a lot of the traditional advantages associated with electronic phase shifters. So those being that it can induce a 360-degree phase shift, as low power, and is relatively compact. So there's been lots of really great work in the field of microwave photonics phase shifters in the past, and they've been implemented with everything from rings to gratings, and more recently PN junctions. But we're very interested in using stimulated Brillouin scattering because of a number of advantages, mainly that it induces a gain-based phase shift, it's easily tunable, it's got a high resolution, which means we can induce a phase shift on even relatively low frequency RF signals. It operates anywhere within the transmission window of the material, and it lends itself to be integrated. And seen here is just a regular SBS phase response. However, if you want to achieve a 360-degree phase shift based on stimulated Brillouin scattering, you need 50 dB of gain. And in any real system, that's a limiting factor. So it's clear a low power scheme is required. So that leads us to the motivation or the aim of this work. So we want to develop a phase enhancement technique to enable a 360-degree phase shift over the broadband using only modest amounts of SBS gain. So going to a bit of an outline, so I'll be talking about the principle of operation of general photonic phase shifters. I'll be talking about stimulated Brillouin scattering, or SBS, and in particular on-chip SBS. I'll be talking about the experimental setup, the RF phase enhancement scheme, as well as the experimental results and the conclusion and outlook. So this is a fairly general microwave photonic phase shifter. So you've got a microwave tone, which is modulated on an optical carrier, and the sideband is removed. And this travels through the system and beats on the photodiode, and the output is a microwave tone. However, if we were to induce a phase shift on the carrier here, the output signal is phase shifted. So to take this idea a little bit further, here we have a carrier and a sideband in the optical domain, and they beat together to generate an RF tone in the electrical domain. And if we induce a phase shift on this carrier, we induce a phase shift on the output signal. But if we move the sideband a little further away, the frequency of the RF tone is shifted. And again, if we induce the same phase shift on the carrier, we induce the same phase shift on the electrical domain, despite being at a different frequency. So if we take this idea one step further and replace the sideband with a broadband signal, we generate a broadband RF tone. And inducing the same phase shift, we end up with a phase shifted broadband tone. So we're inducing this phase shift with stimulated Brillouin scattering. And here you have two optical counter-propagating signals that pass through a waveguide called the pump and the probe. And they interfere to generate a grating. So the pump scatters off of this grating and coherently amplifies the probe. And this induces a gain and phase shift on the probe. And we can do this in a chalcogeniide waveguide, which guides both the optical mode as well as the acoustic mode. And we want to do this for a number of reasons. Largely that it has a small footprint, it's robust, it's optically stable, and because of the very high confinement factor, we're getting 500 times larger Brillouin gain than in single mode fibers. So this is some really nice work by the Sydney group, and here they're using an integrated chalcogeniide platform to generate a broadband phase shift using stimulated Brillouin scattering. However, they're limited due to gain, or the available gain, and they're only able to achieve a 240-degree phase shift. So this is an experimental setup which is very similar to the one that I just showed you. So the way it works is this. So the laser generates an optical signal which propagates through the phase modulator, which is modulated by our input RF tone. This passes through the waveguide before going through a circulator and a filter which removes the sideband before beating it at the RF output, which generates a signal. And on the other arm, it passes through a dual parallel Mach-Zehnder modulator, which is then amplified by an EDFA as well as being filtered, and this counter-propagates through the waveguide inducing the phase shift. However, if now we add a second laser, which passes through the phase modulator, which is modulated by the same tone, which propagates through the device, but is completely unaffected by the pump on this side because of it being at a different frequency, and as it passes through the bandpass filter, the opposite sideband is removed. This gives us a phase enhancement, and I'll show you how that works here. So this is going back to the single laser system, and here there is no pump acting on the signal. So we've got a carrier and we've got a sideband, and this beats together to generate an RF tone, and we're going to call this phase 0. And if we turn on the pump, this generates a phase shift here, and this induces a phase shift on the output RF tone. But now we add the second carrier, which is 180 degrees out of phase. So you can see the resultants here, which is this small green one, and it's pointing in the opposite direction. And now, if we apply the same phase shift as we did a few moments ago, we can see here that the phase θ2 is much larger than θ1. And this is the core idea of our phase enhancement scheme. And this works in the opposite direction as well. And so here, θ1 is smaller and θ2 is again larger. But it's worth noting that it operates in the opposite direction of the original one. So just to demonstrate what I've just been talking about, here is the phase profile of the single laser system as we sweep through the SBS resonance. And when we turn on the second phase enhancement laser, we can see that there's a phase enhancement factor of 10, which gives us a 360-degree phase shift. So this can operate in the broadband as well. And this is some very nice work from the Harris Corporation. And they've demonstrated a 65 gigahertz bandwidth and a phase enhancement factor of about 5. But it's worth noting the only limitation here so far has been the speed of our various components. And a good way to visualize this data is by plotting these vectors on a complex plane. And you can see the phase shift here is given by theta taken relative to the origin, which is highlighted here. And when we induce the phase enhancement plane, here we can see that the output data then moves to encapsulate the carrier, the origin. So this is where we get our 360-degree phase shift from. And you can see here that the relative vector between the origin and these points is relatively constant, which gives it a relatively flat response. So, yeah, and you can see here it just shifts between this side to encapsulate the origin. And we were able to demonstrate this on an integrated platform as well. And so here, using only 11 dB of SBS gain, and 19 dB of on-chip pump power, we're able to generate a 360-degree phase shift up to 20 gigahertz. And we were limited here by the speed of the various components, and we could potentially push this much further. So that takes me to the conclusion and outlook. So we were able to demonstrate an order of magnitude phase enhancement up to 360 degrees. We're able to do this both in fiber and on chip. And we were able to significantly reduce the power and gain requirements and demonstrate an ultra broadband phase shift up to 65 gigahertz. So some of the advantages of this scheme is that it doesn't rely on a large SBS gain. And this gives us the option to move to other materials which might have some other favorable properties, like silicon because it's CMOS compatible, but that doesn't give us very much SBS gain, as Ben alluded to yesterday. And another advantage is that it can be applied to other phase shifting schemes. It can be completely independent of stimulated Brillouin scattering. So it can be used for such things like thermal phase tuners. So thank you very much. I'd like to thank the funders.
Thank you very much. Time for a question.
Thank you very much for this excellent presentation. I saw that the change in phase induces an amplitude variation to go along with it.
It does, yes.
Is there a way to compensate for that?
Well, in many instances it's useful, but it comes from the Kramer's code relation. But if we go back to this work here, hang on. So with SBS, there's a gain resonance, but on the opposite side, there's a loss resonance. So if you were to put in a second laser, you could use the gain and then the loss on top of one another to give a very flat amplitude response. So there are options if you wanted to do that.
One more question over there.
Just a quick question. When you compare this slide with your final slide, it seems that the ripple in the phase is much higher with the, yes, this one.
Yeah.
Do you have an explanation of the ripple we can see on the...
Yeah, we do. So when we were doing the single laser setup here, shown on the left, we were just using a regular bandpass filter, I suppose, and it had very low insertion loss, and as a result, the link gain was much higher. But when we wanted to do the dual bandpass filter, we needed to use a wave shaper, which has much larger insertion loss. So that's one potential location where that could come from. But the other issue is, if you go back to this diagram here, you can see that there's an inherent trade-off between link gain and phase enhancement. So this net resultant vector here, I mean, this is only a graphic to demonstrate the idea, but even still, it's much smaller than these other vectors. So the trade-off is link gain for phase enhancement. So that's another potential source, because when you're dealing with only one laser, there is no such destructive interference.
So I think we should just start.